once again, it's a pleasure to talk to you about my work. Just see if it's yeah, perfect, it's working. So I come from University of Calgary. I'm a head and director of Biometric Technology Lab since 2003. And much more recently, we moved in to cognitive systems design combined with biometric technologies, multimodal decision-making, applications in medicine for deep learning, also involving look into social networks and the way how we can process big data accumulated on social networks in our research. Here's just a snippet of mainly textbooks and conferences that I've been involved with. I started the conference series in the International Conference on Computational Sciences, an application that's been gone around the world 20 times by now, and that was started in 2001. And I'm also editor-in-chief of the Transactions of Computational Sciences journal associated with Springer LNCS series associated with that conference. Also an editorial board for IEEE transactions on social networks, IEEE Access journal, as well as the Visual Computer journal. And essentially, textbooks, titles, kind of outline what I was working in a computational intelligent geometry-based approach where I started, multimodal biometrics, intelligent image processing, and image pattern recognition for biometrics. So I would like to just bring attention to one more event. Following this conference, I'm currently very, very busy being a main chair of the Computer Graphics International Conference. It's the oldest computer graphics conference in the world. It's the only official conference of ACM and Society on Computer Graphics, published in ACM, as well as Springer Lecture Notes Computer Science. This is coming to Calgary and Banff this June. So obviously paper submissions process was closed, but we have very good special rates for guests and visitors if you would like to visit this after. Sorry, I had to do this little plug there. So essentially, I will discuss why we do what we do, and this is research that we do in Biometric Technologies Lab. So we look at person recognition. So how do we express ourselves through our face, our fingerprints, the way we walk? And also we try to explore a little bit beyond those horizons. So we see if we can understand the mood or the emotion of the person just by the way how we sit. So we're looking at the posture of the people. We use Kinect sensor device. So essentially, for everybody right now, we're trying to understand based on your structure of the body, based on the tilt of your head, based on how much space you take, without even facial expression, what are you feeling? Are you happy? Are you satisfied? Are you interested? Are you bored? Etc. Etc. We also try to understand what is a person presented by the way they walk as well. So we can see if we can identify some diseases. I'm going to touch base a little bit at the end of this presentation on how we try to estimate posture for physiotherapy purposes or estimate amount of pain in the body. And this is just one of our recent projects. And the last thing that we try to do is we try to also understand whether by our social network communications or day-by-day activities, checking out, checking your banking account, for instance, or contacting with your family, friends, or uploading some papers to ResearchGate, etc., whether those activities are individual and represent behavior of individual, and whether we can understand the gender of the person, the age of the person, connections of the person, or even intent of the person based on those social network communication without having physical or behavioral traditional biometrics. So we can see that we're working with thus collaborative and social environments and applications like situation awareness, smart devices, personalized services for banking, and risk prediction. Obviously, we have a number of colleagues and collaborators for this research. So we work with IBM and Microsoft. We work with ATB Banking. We work with NVIDIA company and BlackBerry's producers of mobile phones. And we obviously present this research as well to National Defense Security of Canada. Just got a big grant to do cybersecurity research in this domain, and to conference such as FBI run conference on privacy and security in New York. So just to give you a snippet and some basic introduction, this is the overall area where I'm coming from. So biometric system is a pattern recognition system. This conference is about data mining and pattern recognition that looking at certain personal characteristics either expressed physically, height, weight, color of the face, color of the hair, color of the eyes, etc., or looking at biological features such as, for instance, the heart rate, the blood pressure, the DNA, or looking at the behavioral expressions such as my voice, my gait, my signature, or looking at the social expressions right now, such as our activities in online world. We can identify who the person is. Right here from the Wikipedia, you can see example of the very first biometric system where normally, typically, criminals, prisoners would be measured for their circumference, the height, the weight, the size of the body, etc. And the very first mentioning of the biometric system was in Mark Twain's book, Life on the Mississippi. So the murderer there was actually identified by the thumbprints he left in the sand on the riverbank or in the clay along the riverbank. The research was advanced by Sir Francis Galton, British anthropologist, that started his observation of fingerprints as a way to identify criminals in around 88. And then the example right here is Alphonse Bertillon body measurement system that later became the Scotland Yard official system for tracking criminals and then expanded onto France and the US. So here we go. This is a lab where we're working with, so we take a number of different measurements, faces, fingerprints, gait, activity, infrared, using the different cameras. And here are the areas, overall areas that I'm working with. So today I chose to describe just two very recent projects for you, just the snippets, very small snippets of our overall work. But this kind of represents the whole areas where we're working. So traditionally, biometric research domain included physiological and behavioral biometrics and included identification and verification. For the past 15 years that we've worked in, we tried to advance this area and expand it to different domains. So first thing that I think I already mentioned, we introduced the notion of social biometric. It was recently published in IEEE Transactions on System and Cybernetics, and also behavior analytics. And this one essentially says that we are very, very habitual in the way how we access internet, when we access internet, and what can be communicated and the style of communication with others. So in this research that I will not be able to share with you, but you can read it in our papers, I'll just very briefly mention we had a couple of discoveries. So first of all, we actually established that this can be used for very precise authentication on the test bed of Twitter users, about 500 of them. We achieved, at the very, very end, we achieved 95% accuracy of recognition just by social measures alone, without no identity of the person, without having their faces, their fingerprints, their names, nothing like that, just activity online over a period of 6 months. Within those activities, the features that we looked at were linguistical features, were content-based features, obviously, group of interest, etc., was a network, friends network, retweet, hash, hyperlinks, networks, and also spatial temporal features, so the time when the person accesses internet and locations from which person accesses internet. So combining those together and using multi-modal approach, we were able to come from linguistic features alone that give only 30% accuracy of identifying somebody, or the friends network alone that gives only 50% accuracy of identifying somebody, which is equal to flipping the coin. It's super random. It doesn't give any, to 90 to 95% accuracy. The most recent research that we presented in this domain very quickly was at this year's in Miyazaki conference in Japan, in the IEEE conference Systems, Man and Cybernetic. It was nominated for the best paper award there. So essentially we said, we're going to look at just time when somebody communicates on Twitter over 6 months. We will remove absolutely everything. So now Like you can imagine, essentially, it's an invisible person, right? We don't have face, fingerprints, anything. There's no body measurements. There's no behavioral methods. And now this person that communicates, right, through online networks, now we remove the content of the communication completely, so the tweets are empty. We remove the friends networks. We don't know who their friends are. We don't know whom they're sending. We remove location of it. All we have is time. And we created 12 different features to identify time interval for how long person staying online, how far. For 200 people, it was giving us almost 90% accuracy of identifying individual correctly in this database. So this just tells us how habitual features are and how interesting and amazing, how many things we can discover just from this auxiliary information. Anyway, we use machine learning and cognitive sciences and fuzzy logic to make our decision making, to come up with research and combine information. And then recently we look at risk analysis and emotion prediction based on this person and perform data, big data analytics. So I have to go faster. I did make the content of this presentation already twice shorter than my normal 50 minutes keynote, but I'll move through the rest of the slides slightly faster. So this is an example of one of these biometric systems. So we have a data set, can be image, which is what traditionally we got used to it. In this case, it's an iris. It can be those temporal patterns of the time somebody tweets. It can be your heart rate, can be anything else. We do put it through the sensor module. We make sure that quality is correct. Then we extract the features. So for the fingerprint, the traditional biometric classification, you have to extract 34 minutia points. And 34 minutia points give you on fingerprint, if it's high quality, almost 99% accuracy of recognizing the person. This is why it's used by law enforcement, so when you cross the border so extensively in majority of the countries. After we extract the features, we store them in the system database, and when the new sample comes, we don't have it labeled, so we can solve two problems, identification or verification. Verification means I'm coming in, I'm saying, hi, Lars, I'm Marina Gavrilova, this is my name, and he trusts me because he saw my picture on the website before, and I speak with Russian accent, so I must be who I am. And that's a verification process. Identification process, if I just walk incognito here and I don't say my name, and then he or somebody else has to identify and map my picture to my last name. So that identification, so it's a little bit harder problem. So this is an example of multimodal system architecture. Essentially, that's what we've been doing for the, from around 2012 to 2017, when it was becoming very, very popular. So instead of using single source of information, we use multiple sources. So in this case, we use face and fingerprint and maybe voice together. We obviously did this research when we used the, let's say, face signature and the social biometrics together, and we got to, as you can guess, 100% accuracy of recognizing an individual, because this is a lot of information on a very large database. So we have the same process. We extract the features, we map the features individually for different modules in the database, and then in the end we have this little module which you hardly can see. This is called the fusion module, and there we can have score level fusion, match level fusion, rank level fusion, or fusion at the sensor level, and each of those actually further on will be classified to logistic regression or weighted sum analysis or Markov chain model, et cetera, et cetera. There is a whole textbook written on just this little block right there of how you do this fusion properly, so you don't lose information and your decision accuracy increases. The analogy, again, because we all come from different fields, it will be with doctor doing diagnosis. So you come to the doctor's office, say, oh, I have a runny nose and I have a headache and I only have it for 2 days, but I don't have any other symptom. And he needs to say, what is the diagnosis? So this the same idea is right here. And we want to make sure this diagnosis is accurate. We identify either emotion or individual or their name properly. All right. So, and then for that, because I promised to talk a little bit about deep neural networks, it's super popular for the last 2 years. It's a buzzword, right? 3 years ago, it was big data analytics. And now it's deep learning in any shape and form. We see it in a lot of research and lots of papers being published. And even this conference will have quite a few very, very good papers in this field. So in this, we started initially with using just neural network architecture for this module. I'll skip that. Sorry, the slide got a little bit corrupted. But that was one of the very first applications. And then we did an interview, I think, to one of the big newspapers and journals when we did it about 10 years ago. We said, well, for our fusion method, we can use neural network to make fusion of the data. And much more recently, we use it in different applications. So the part that I just described before is what we normally do and where we contribute in this domain. Right now, 2 little case studies. So only 2. So this is case study number 1, probably in about 5 minutes talk about it. Gender prediction using image aesthetics. So what is it? So we try to venture a little bit more unknown, and just similarly to our research that I didn't describe here on the social network identification of the person from the tweets or the activity on the network, there are users of the Flickr. So there are 40,000 images that was sampled by 200 Flickr users over time. This data set was not collected by us. Right now, we're trying to recreate it, and we try to collect a little bit different one. But this was collected about 4 years ago in the University of Bologna, Italy. And what essentially you can see is right here, these are the images that were presented in the data set. They were unlabeled, and they were just photographs, images that you can create, works of art, portraits, landscapes, etc. So the users were asked to identify and choose 200 images out of 40,000 that they like, and that's it, not rank them. And after that, we run process and algorithm. We try to extract the features from those images, and we try to answer 2 questions. One is, can you identify the person just by the set of images that he likes? If now we have a next 100 images, a person identifies that they like, can we say that this name of this person is Marina Gavrilova or Lars or somebody else, just by their visual aesthetics? So that's the research was never done before. And the second question we asked, also the research that was never done before, as far as we know, is can you tell whether it's male or female based on what kind of pictures you like on the Flickr, on the social media? So we actually answered this question positively when we started this research, and I think it's the best part about us being researchers. We had no idea. I mean, if nothing comes out, nothing comes out, right? Maybe there's not enough information in those images. We got accuracy up to 90% on both identification of the person and understanding whether it's male or female that likes images based on the data set after some training. So I'll show you just a little bit quickly of how we got there. So there's the question, if you'll have favorite pictures, can we predict the gender? It's a little bit lagging. There we go. So essentially, we're looking at different preferences, different cognitive abilities, different perception of the people, and previous research shown that this actually the people are very habitual features, so we might find something there. So there could be different preferences for different features that we just need to dig deeper and find out. Slightly slow, just have to, yeah, there we go. Just gonna skip that because I just explained to you what we did. So essentially at the end, after we read all the literature on the images, we extracted 56 various features. And if I read some of this for you, for instance, it can be contrast, correlation, energy, homogeneity in the images. It can be preference in the colors, so predominant color scheme, pink, red, blue, etc., for some of the people, some of the images. It can be, what else? Smoothness of the images and sharpness of the edges, and also contrast and symmetry. And then there's lots of other features that I cannot explain in a common terms that normal human would understand, but this is, first and second derivatives and normals that were extracted by applying histograms and looking through the different channels in the images. So some of them were more technical, not visible to the naked eye, and some were visible to naked eye, such as symmetry and the edges and the colors. And once we created this set of 56 features, so the first project we decided to do is a mixture of expert models. So at this time, when we did this research 2 years ago, the deep learning wasn't quite yet that popular. So we went with classical machine learning methods. So we use support vector machine, k-nearest neighbors, Bayesian networks, decision trees, etc., etc. So we run all of those classifiers. We fine-tune parameters, obviously, for the given data set. And once we run them all, We also created probability models, so probability of this person being female, probability of this person being male, and then control the influence of which classifiers were the weighted model to make our decision, a final decision, whether it's male or female. So SVM, KNN, and decision tree was the three most prominent, best classifiers that give us best rates. So we kept those for our expert model. And when we did our classification, here are some of the results. So for the decision tree, which we just use it, you get 71% accuracy for SVM, 70, for KNN, the worst one, 66%. Then after we choose features that we're going to feed to those classifiers. So out of those 56 features, those huge tables that nobody could see, we picked certain classifiers, like about 20 to 25 for each of those. We did the selection using genetic algorithm, so we got improvement by about 6% on all. So we got now for decision tree 78% accuracy of identifying gender, which is more than random, clearly more than random, not too bad, and 76 and 79 for KNN. So that shows right here which improvement we got. And then at the end, so let's flip the slide. So the only thing. So we performed adjusting of the weights in our final model when we combine those, expert model classifiers. So we can adjust the weight simply by saying, okay, we're going to give 2 weight of 2 to the best classifier. In this case, it was already KNN, then like 1 to the next one, and 0.5 to the worst. Manual weight assignment doesn't work. So once again, we run the genetic model on after about 100 generations, we got to the best weights assigned, and the final accuracy of prediction was 82.5% after running genetic algorithm model to actually identify the gender of the person, whether it's correct or incorrect. So it's correctly found predicted gender for 99 users. Another thing that we did, we actually looked at those features and we understood which features correlate to men and which to female. And so for female, normally, as you would expect, there was softer colors, softer borders, and for men, it was more symmetry and much more prominent ages and colors like black and white and contrast. And some other features was also predominantly those features that identify those genders. All right, so case study number 2, in which I'm going to finish it, is physical rehabilitation and Kinect. So I did spoke a little bit in the beginning about how we can identify the person by the way we walk. We can potentially identify if somebody's in pain or upset or unhappy by the way the pose is structured. And we just finished the work that we're going to present at Computer Graphics International that took us literally 2 years to finally get accepted to that conference. On the sample set, we can identify 5 emotions of the person by the way, if we just have a recording of 20 seconds of how they walk. And we got pretty good results using combination of convolutional neural networks and expert models on this. So here's our data set. Once again, I chose some very, very visual images to present for you. So we have a grayscale, we have colors, depth stream, and also we have a wonderful tracked skeleton and a 3D space. So we started to do this Kinect research when Kinect, we got it from Microsoft. We worked with them directly on using the APIs and version, and then Kinect was supposed to be phased out. So we're like, what are we going to do? Now we have to find another sensor. And now, as you know, Kinect is coming back. Kinect Azure is going to be released or already released for researchers in May, June this year. And this is specifically for research community, not for gaming industry anymore. So if you want to sign up, the Microsoft has an open, try to sign up and use those devices in the research. So in this particular case study, we just collaborated with Microsoft, with a little company that develops software, Physio3D, for physical rehabilitation, and the actual practitioner clinic in Calgary that sees lots of patients that come with different injuries or pains in the body, and they try to correct it. So what we did, I can see Lars is standing, so I have to wrap it up very quickly. So just to give you a summary of what we did is we first of all obtain and record the posture of the patients. We remove the noise from the signals. We apply different correction on all the joint parts. This is how humans look when you do it through the steady gait cycle. And then, because I promised to talk a little bit about machine learning, so in this particular case, we just created a very simple convolutional neural networks with 3 different hidden layers and the final softmax decision layer. More details on dropout rate and activation you can find in our paper on this research. And essentially the goal, let me just give you a summary. The goal of this was to try to do what the doctor, physiotherapist was doing for 30 years, so he has experience in 30 years. He looks at the patient, he takes a measurement, he said it's going to be easy, average, or difficult case to treat, and he knows how much time and how many sessions he needs for the physiotherapy. So we plugged this information in our system. We got his knowledge in convolutional neural networks. We had sample cases, test cases for number of patients, X number of patients, but remember how many. I think overall was about 30, and then we tested it on the other data set and see if our system, looking at the same measurements, can do the same prediction. And here are the results, the drum roll, please. So we had one person to try to learn on the system with simple, 24 average, and 4 complex cases, 29 in total, used 10-fold cross-validation and average accuracy on correctly identifying on a test set now whether the patient will be easy, hard, or difficult was 99%. So essentially, in about 2 months, we were able to just recreate this knowledge of the doctor and put it in the system and get 99% accuracy, but the doctor was very good. So, but it essentially shows the possibilities and capabilities of modern systems to tackle some of the current problems. All right. Obviously, there's lots of work to left over in all of those fields. We are exploring intention, emotion, stored in the body, stored in our communication more and more through the next work. And in conclusion, we can see, and you will see it through this conference, I'm sure, that there's lots of machine learning, and there is almost unbounded possibilities to apply this knowledge, but you have to apply it in proper domains and with enough intelligence so that it works. I described that we can use a single source of data. If you use more sources of data, information for decision making, it can be very useful. Obviously, we also brought in social studies, interaction, communication, even using our aesthetic preferences into the domain of identifying a person. And at the end, there's a huge number of applications that we're tackling in virtual reality, game design. We have a project with smart home business. We have a project with ATB banks that try to understand the emotion of their customers, et cetera, et cetera. So there are almost unlimited possibilities to extend on this research. And with that, I will wrap up.
Let's give a big hand for Professor Gavrilova.
Thank you.
Thank you so much.
Thank you.